So, hello everyone, welcome to the class number 7 in Calculus grade 12. And today we are going to practice with problem solving involving limits and derivatives. We're going to prepare for our test this coming week. So, Alan, I would like to start today's class with question from the very first chapter when we started studying the limits. And I want you to basically use both ideas here because, as we know, limits and derivatives are pretty much about the same thing, right? But knowing how limits are working, we can develop some patterns to use derivatives more efficiently. Basically, finding the limit of any function much faster. In the test, you may have one task that's going to ask you to find the limit of the function, or I'm going to ask you to find the average rate of change. You see, like here. I may not say directly, like, find the derivative. I may say find the instantaneous rate of change. And I can ask you using the limit function. If you would use the limit function for this, can you remind me the derivative definition in limit terms?
Yeah, it's limit h to going towards 0 is f x plus f of x plus h, subtract f of x, subtract a, divided by h.
Subtract f of x. Okay, great. And while we know this function, we can use it basically in any case. No matter how long is the equation that we are looking at, we still can stick it into our well-known formula that we discovered. Okay, so let's start solving this task, knowing that we have this limit function. And I like this type of exercises when we are talking about some, physical stuff, something that may really be happening in the real life. So question is, the height of a model rocket in flight. So I'm gonna draw it like this. I have a coordinate system, okay? Right away, what I know, height of a model rocket. So we establish, this question establishes equation to find the height of the rocket at any moment of time. Okay? Do you understand that?
Yeah.
So basically we have h for height, and h in our case, it's pretty much the same as y, the function, right? The dependent. And what would be instead of x in this case?
It would be the speed or seconds, time and seconds.
Yeah, time and in seconds, and let's say height in meters, right?
Yeah.
Meters. So h is a height in meters at t seconds. Great. We know the equation. Imagine we are building the rocket, and we came up with following equation about that, how it's going to fly. Determine the average rate of change in the middle rocket's height with respect to time during the first second, the second second. Determine the, when I read this question for the first time, I'm also kind of confused. Middle, what are you talking about? Let's look at it again. Determine the average rate of change in the model rocket's height with respect to time during the first second. So what they're asking us is to find the average rate of change. That's right away what I'm picking up. If they ask for average rate of change, it brings me an idea of the limits right away.
Yeah.
If they would ask me for an instantaneous rate of change, what would you do?
Wait just a second, give me a second. Instantaneous rate of change? Same thing, it's in the same formula.
Exactly, average rate of change. Now, sorry, instantaneous rate of change would be the either the limit formula or the derivative of this function, okay? It would be h prime of t, right? Sorry, I made a mistake when I said that the average rate of change is calculated by the limit function, because if you remember, in the average rate of change,
There's
we,
no limit.
yeah, there is no limit because we are not taking two very close points. When we are looking at the average rate of change, we are making a second line, right?
Yeah.
Between these 2 points and evaluating this angle, basically. The slope of this, the average, let's say the slope of the second line that connects 2 points of the graph. And do you understand why the rate of change, basically, it's about an angle? Can you explain me why is it about an angle? Don't worry, yeah, we didn't cover this, but it's just interesting fact because as soon as we just both to us, why not? Because I find it's really interesting and it should give you an idea about that how math works. Because what you're doing here, this is delta y, right?
Yeah.
This is going to be delta y, and this is going to be delta x. Doesn't it remind you something?
Trigonometry.
Exactly. For me, it basically reminds me a triangle, right? So we can build it either like this, or we can just move delta y here. This is also delta y, right? It's the same as this delta y. You see? So basically what you're getting here, you're getting 1 point, second point. Difference between them, it's delta y. It could be even here. And you get delta x. Here or here, right? And you have this hypotenuse. That's how I look at it. Do you remember from the geometry?
Yeah.
The hypotenuse, this is the right triangle. So basically, when we're dividing delta y over delta x, we are finding the tangent of this corner. You see? Of this angle.
Yeah.
Because tangent is the opposite side divided by the
Adjacent.
you see? So m, the slope of the curve, it's basically equals the tangent of the corner. You see? And if this tangent is negative, if you remember the trigonometry, tangent would be negative. I believe it looks something like this. So tangent of 45 degrees 1, right? Then it's getting less and less. Here is going to be equal 0. And here is going to be negative in this quadrant. And when it's negative, we can see that this arrow pointing down. And on the graph, it would look like from left to right, from the lower value of x to the greater value of x, delta y is going to be basically negative. We are going to go down, you see? And you know that the tendency of the graph when the instantaneous rate of change has is a negative, it means that the graph is going down. It means that the function is decreasing when x grows, right? So it would be the case with 1 over x. If it's 1 over x, you know, it looks like this. It's not crossing the y axis. It's just approaching it. And you can see that it goes down, right? And if you look at the derivative of this function, it would be 1 over, it's x to the power minus 1. So subtract 1. So times minus 1, right? N. This is a power rule we are applying here.
Yeah.
If we're applying power rule, we have minus 1 divided by n, by x squared.
Okay.
And in fact, you can see that the tangent is going to be negative for all positive x's and for all negative x's as well. Because if you have negative here, if you have negative x, it's getting squared. So it's becoming positive anyway. And the multiple of minus 1 is always going to give us negative tangent. Okay? A bit of like remark about idea of this limits and whole stuff. I just wanted you to show that everything interconnected. You see, you learned geometry at school, and now you see why these tangents are useful. So let me clear all this stuff. And did I give you enough review? Can you solve this task for me?
Yeah.
You can solve it right away, or you can say me what to write.
I'll tell you what to write because I can't write as fast. So it's gonna be.
So
it's
let's focus on the question.
the
The
formula
first.
down first. So it's gonna be f of x plus h. Subtract f of x over h.
Okay.
Now you would sub in your equation, this equation into your thing. So it would be negative.
I would like to highlight one thing. Sorry, that you see function is h of t. So you can write this in the first line as like formula. Then you say equal to h of t plus h. Subtract. I won't deduct marks for this, but somebody else may. Okay. Like this. You see, we have too many h now. Let's call this something else. Let's call it not h, but delta t, okay? Just difference of time. Because h is difference of variable, right?
Okay. Can we write that's a bit too many t's then.
Not at all, not at all. Because
yeah, whatever. It's
this
fine.
this t is a variable, and this t is a difference between 2 points.
Yeah, it's fine.
Delta t, it would be t2 minus t1.
Okay, I can still understand it. So then it's gonna be negative 4.9.
Just wait a second. Are we going to stick values right away, or are we just going to write the formula first, the equation?
We're gonna write the equation first.
Okay.
Negative 4.9. H t plus delta t squared plus 25
Yeah.
t plus delta t in brackets plus 2 subtract the same equation.
Sorry, I just transferred it in a weird manner.
No, that's fine.
So what's the next step?
Negative 4.9 t squared plus 25 t squared plus 2.
Why t squared?
Oh, no, not t squared. Sorry, no. I made that was a mistake.
Are we missing something?
Over h or over delta t.
Not just that. You see, here you have minus in front of the function. So you have to consider it as a brackets.
Yeah.
And
Oh, yeah.
once you open them, this plus is going to change to minus, and this plus is going to change to minus 2.
Yeah. And then, I mean, you have to expand it then. So it's going to be negative 4.9.
Let me do this. Can you see it clearly?
Yep.
So
Negative 4.9.
just give me a second.
Yeah.
Let me give you a hint. Prior to expanding something like this,
We should
definitely something going to simplify.
Yeah, we should simplify it first. So it's
Mm,
going to be negative 4.5.
let's open
B.
these brackets first,
Yeah. H.
and it would be minus. Okay, I'm opening the bottom brackets first. 4.9 t square plus 25 minus 25t. Yep, minus 25t minus 2 minus. Oh, wait. Sorry, I'm gonna move it a little bit lower. Minus 4.9 times you know why I don't want to expand this bracket right now? The
Yeah, because
quadrant, like square of product, because it's gonna be t square plus 2t delta t plus delta t square. You see?
yeah.
It's just overwhelming. Let's leave it as it is in the brackets, okay?
Okay.
We opened the second brackets. Now we write t plus delta t square plus 25 t plus delta t plus 2, right? All divided by delta t. And remember, if we searching for instantaneous rate of change, you definitely need to expand all this first, because only by that you can simplify this delta t that is going to travel to 0. Remember? Because in the limit, delta x or delta t, wherever, travels to 0, or h travels to 0, it's all the same.
Yeah.
You cannot divide by 0, so we want to simplify this. And then, because this value is super close to 0, we can substitute in the nominator some values for 0 and simplify it and get the answer. Oh, no way. No way. Yes, undo. Great bottom created by people. So let's keep on solving this one. So just for your convenience, don't expand these brackets right away, because if you take a look at the question, now we can start solving the question itself once we get the formula, basically. This would be the formula for the average rate of change between any 2 points of the graph, right?
Mhm.
So look at the last sentence of the question. Determine the average rate of change in the model rocket's height with respect to time during, you see, during the first second.
Mhm.
It means that the rocket took off and was flying for 1 second. So we know that when the rocket starts going, t equals 0, and in 1 second it's going to be t equals 1.
Mhm.
So it's t2 and t1.
Mhm.
Now, knowing this, you're just gonna stick in these values into this formula, and you're gonna see how much easier it becomes, because t, the starting point. Remember, t in this equation is going to be the starting point. T
Mhm.
plus delta t is gonna be t2. This is t1 plus delta t.
Okay.
Now you substitute t1 equals 0 in this formula, and look at the magic. This one turns into 0. This one turns into 0 because it's multiple by t, which is 0 in this case. Minus 2 is going to be simplified with plus 2. These brackets becomes even easier because 0 plus 1, because delta t is equals t2 minus t1, which is equal 1. You see it?
Yep.
So now you substitute t1 equals 0 here, 0 plus 1 a square equals 1, right? Do you understand?
Yeah, I understand.
Great. So this one is just going to be minus 4.9, blah, blah, blah. Then you simplify it. Delta t is going to be substituted for how much?
Delta T
Yeah, delta t.
1.
Great. So divided by 1. We don't even need to simplify anything. So the derivative, so the average rate of change would be minus 4.9 plus 25, and it's equal 20.1. At that, this would be average rate of change.
Wait. Sorry, how did you get? So with the, let me just
Take a second look. So again,
right here.
you found the formula for
What did
the
you do right
average
there?
rate of, pardon?
What did you do right there?
Where?
Where I underlined it?
Oh, this is t
Yeah.
plus delta t. And as soon as t equals 0 and delta t equals 1, 0 plus 1 a square equals 1.
Oh, and same thing for here.
Yes, here just we're not squaring it, just 0 plus 1.
Oh, okay.
And this times 25. So 25 times 1, 4.9 times 1.
Okay.
And you see, you didn't, because you're looking for average rate of change, you don't need to expand these brackets. Keep it in mind.
Mhm.
So during the second, can you just in words explain me how would this whole solution be different if height with respect to time during the second?
Yeah. Give me a second. I'm just writing it down on my book. Okay. Well, you would, instead of replacing um t with 1, you'd replace it with 2. No, delta t. You'd replace it with 2 instead of 1. So then it would be
I would read the question.
the second.
So not the during first 2 seconds,
Oh,
but during
one.
second.
So
So
1 to 2.
T1 would be
1.
1 and
Oh, okay.
T2 would be 2.
And then the t would equal 1,
Mm-hmm.
and then delta t would equal 2. You'd have to solve that.
Delta t is not equal to.
Then what is it equal to?
If-
Oh no,
Let's,
it equals to 1.
yeah, exactly. Difference
Yeah.
between these two values.
Yeah.
And you can visualize it for yourself. T plus delta t is basically equals t2, right? Makes sense. Because this is time after some time passed, you see?
Hmm.
Some time passed, it means this is second reference point. In the other case, you won't have time here. If I change this for x, it won't change anything. If I say instead of rocket, the snail is flying, it would be exactly the same.
Hmm.
You see?
I'm just writing it in my book. That's why I'm quiet.
Yeah, sure. Let me know as soon as you're done. So, oh, sorry. This is this task like this would be in the test, okay?
Okay. T1 equals 1, T2 equals 1. Then you would one plus 1 squared plus 25. 1 plus 1 plus okay, all over 1 would be 4. So we plus 50. Okay. Okay, I got 10.3.
Okay.
Hmm.
10.3.
Yeah.
Oh no, it's good. And first I got confused because I see, look, I see it's exponential. It's
Yeah.
gonna be parabola. But, and I think, wait, if it's parabola and we go right, so it should grow, right? Over
Yeah.
time. But then I see it's minus. It's negative parabola. So it's gonna be upside
Yeah.
down.
Yeah.
So it's gonna be upside down. So let's say, can you tell me what would be the height of the rocket at the 0 second?
2.
Exactly. So I don't know. We would start as soon as we know that when we go farther right over the graph, we're getting the rate of change getting lower, right?
Yeah.
So I believe like we should be here because oh wait, It's actually, wait, you say the rate of change. Take a look here. Basically, what we're studying is the rate of change, right?
Yeah.
So rate of change is positive. So rocket is flying up. It's not going under the ground, right? It's increasing its height.
Yeah.
And to increase its height, we should be somewhere here. You see?
Yeah.
We're gonna start here, and based on what you know about parabola or just visually observing, you can see that rate of change would slow down as soon as we get closer to the top. You see?
Yeah.
Can you see that? Because if we draw a tangent line here, it's going to be like this. If we draw a tangent line here, it's going to be like this. And on the top is going to be like this. So you see, like, it's like something getting over the peak, and then it's going to drop down.
Mhm.
If I keep drawing the tangent lines, you see, now I start going down. And on this example, I would like to cover one really important thing, that if you can use this whole stuff to find the perpendicular line to the tangent line at the point. Because for two tangent perpendicular lines like this on any graph, they're basically, if this is x, you see, this is going to be slope of the first line, and this is going to be slope of the second line. You see?
Yeah.
And there is one cool property of these perpendicular lines, that the product of their rates of change, basically slopes, is going to be -1. You see?
Yeah.
So basically, it has the same speed of growing. This one has the same speed of growing, right? In the same rate of change as this one, but this one, instead of growing, it's decreasing with the same rate of change. You see?
Hmm.
It's basically gonna be m1 equals, now you just look at this formula. This is so easy to remember because m1, m2 equals -1. Then you can find m1 as -1 divided by m2. And let's say we found the rate of change at any given point, okay? Let's say it equals 5. m1 equals 5. This would be m1, okay? And this would be m2. Now to find it, it's super simple task, right? m2 is going to be equal -1 divided by 5. Do you see that?
Yeah.
Multiplying by m to the m2, both sides, then dividing by 5, both sides. That's how I do it.
Okay.
So write this formula down. You may have question with this part on it. It's just super simple, super simple. It gives you just one additional step. When you found the derivative, please find the perpendicular line to this point.
Okay, so that's so to find perpendicular line to be that.
Yes. First thing you do, you find the rate of change of the given graph at the given point, right?
Mhm.
Then you're sticking the value in this formula, and you find the instantaneous rate of change of the second graph.
So what numbers would you plug in for that equation?
For this one,
Yeah, the M1.
let's practice derivative.
Okay.
So because derivative gives us m1, right?
Yeah.
So the derivative of this function would be first one, power rule. It would be 2 times minus 4.9 times t. I'm gonna clear it up, okay?
Yeah.
Times t, because n minus 1 equal 2 minus 1 equals 1,
Mhm.
plus 25 plus 0. Derivative of a constant is 0.
Yeah.
Here, t to the first power, t to the 0th power equals 1. So now, let's say at the second point, okay? At the second, okay? T equals 2. Find me, and the question would look like this. Find the perpendicular line to the tangent line at the point t equals 2. Because basically what you're doing with this, you are looking for the instantaneous rate of change of a tangent line, right?
Mhm.
So this is it. T2. Now we found the derivative. Now we're sticking in this value in here. And it would be 4 times minus 4.9. And it would be 4 times 9 is 36. So it's going to be 19.6 negative. Can you double check it?
So 4.9 negative
Yeah, times 4.
times 4. Yeah, it's negative that, and then it'll be plus 25. So
Yep.
5.4.
So the answer would be positive 5.4.
Yeah.
And now, next step, you already know it. Stick it in this formula. And this one. And evaluate them too.
Oh, okay.
So it's not complicating the task so much. Just ask, it basically asks you if you know this formula. If you
Okay.
know it, it's so easy. 5.4 equals minus 1 over m2. Next step, minus 1 divided by 5.4 equals m2.
Yeah.
You see, you don't even need to evaluate anything.
Yeah. Yeah. That's easy.
Okay, great. Let's move on. We have so much to do. Sketch the graph. Are you familiar with how to sketch the graphs?
Yeah.
Okay, we won't waste time on it. Draw a tangent line at the point. How would you find this point?
Well, you have the x value, and you have the f of
Function.
x.
Yes, great. Just stick it in. We find this point. It would be negative parabola again.
2 squared times negative 2 plus 4.
It would let's talk about the ways to solve it, because mathematics behind it is pretty much simple. Evaluation is simple. Draw a
Mhm.
tangent line at the point. Okay, let's say wherever. 5 somewhere, let's say here. This point would be here. FO5. And tangent line is like this. And estimate its slope. Do you remember how to estimate the slope?
You assume that h is 0.01.
No. You draw a table. In the middle, you write the value of x.
Oh, and you get the numbers
Yeah,
before.
and you're getting closer to this point. 4.9. You see?
Yeah.
Let's say 4.8. 4.9999. And
Do you really
you
have to
find
go
and
down that
you
far?
huh?
Do I have to go down that far, or can I just choose like 0 point
Yeah,
or
yeah. You just need to choose. Look, they
1?
ask you to estimate its slope. You are a cool student. You already know the derivatives, the limits, you see. But core idea behind all of it is that you don't even need to know limits. Let's just get as close as possible to this point as we can. And from other side, okay? Here, I would recommend you in this one use the number that you're giving this, the point. I'm gonna call it n. 0.0001. The more zeros, the better, okay?
Okay.
Rule of thumb, 2 zeros is enough. Here would be 4.999, okay? And what you do is that you're gonna find the average rate of change between these 2 points and between these 2 points.
Mhm.
And you're gonna see the value in the middle that kind of like, you know, that we are approaching.
Mhm.
And this would be your answer, then estimated slope. Because here, let's say you're gonna get some value like 14. I don't know, I didn't evaluate it. 14.8. And to
Mhm.
the left, you're gonna get 14.9. You see that
Yeah.
it's somewhere in between them because
Yeah.
we're super close to this point. And I'm just gonna add them up and divide by 2. You see, it's gonna be 14.85. Well, somewhere around that.
Mhm.
This would be my estimated slope. And in fact, you don't need to take 10 values, 5. It just in class for practice, we took a look at how the second line is getting closer and closer to the tangent line that we're looking into.
Mhm.
Remember when we draw many seconds here, eventually some seconds are going to be, let's say this is our true tangent line. I'm going to change the color. This is our true tangent line. And if we take many seconds, like 1 point here, 1 point here, then 1 point here, 1 point here, you see, the closer we get, the closer we are going to be to this true instantaneous rate of change or the slope at a tangent of a tangent line.
Mhm.
Is it clear?
Yeah.
Great. Estimate the instantaneous rate of change in fx when x equals 5. You see, it's again, estimate the instantaneous rate of change. Same one as estimate its slope. Pretty much the same. Yeah, but instantaneous rate of change. Again, yep. So for this one, difference between these two questions. This may not be in the test. It's kind of not interesting. So for this one, you would estimate a slope by taking value to the left and to the right, okay? And getting these values as close to each other as possible. For the instantaneous rate of change, you're gonna take 4.9 and 5 and 5 and 5.1, okay? So slope of this is going to be close to this, and somewhere in between, again, would be instantaneous rate of change at this point. And using this method and this method, you're gonna get pretty much the same approximation.
Okay.
You see, because on your math, on your approximation, 4.9 and 5.1 and 4.9 and 5 is not a big difference.
Yeah.
Pretty much the same, just the idea of approach is different. Okay. Oh, Alan, let's go through this tables real quick because it's simple. Just tell me at what point this function is not differentiable, all of
Okay.
these functions.
So for A, that is not differentiable. Give me a second. I just remember seeing it and it's not. I have to figure out why it's not.
To remember why it's not differentiable, remember the definition of a limit. When we approach the point from both sides, something should be fulfilled.
Um, I can't remember.
So, basically, to answer this question, you don't need to know any of the definitions, okay? You just need to know that the graph is differentiable if we can draw it without taking
Oh yeah,
pen
yeah, yeah.
of the paper. If you gotta do like this, it's not differentiable here. If you gotta do like this, it's not differentiable here. You see, we have jump.
Yeah. So it's
But let me remind you the rule. It's pretty much important. When limit, let's say we're approaching A, this point, A, you
mhm,
see, we're approaching point A from A plus, it would be to the right. And let's say we have our formula, like M, right? This is the basically what limit gives us, right? M. Slope. Slope of the tangent line as we approach this point from the right should be L. It's going to be of a limit, okay?
huh?
And limit for A approaching A from A minus, so from the left side, should be the same.
Yeah.
If this is different, if L1 and L2 are not the same, then function has no limit in the point and is not differentiable.
Okay.
So for the existence of the derivative at the point, you can remember it as, so for derivative to exist, function should have limit at a point and limit from left and right side to this point should be the same.
So the first one is differentiable. The second one is
No,
not.
wait. Why is this differentiable?
Because there's 2 points that because L if you to mark the -2, then L1, L2 would equal the same.
Um,
Or is it the opposite? If they equal the same, it's
look, if you just look at the angle here, you see?
Yeah.
It's like this. An angle here, it's like this. You see, they're somehow different. They're not the same. Because the same angle would be if continuity of the graph would be like this. It would be straight line, right?
Yeah.
This angle was equal to this angle. But you remember the tangent line?
Mhm.
Basically, tangent line to a line, it would go like this, right? To the left of -2.
Okay.
And to the right of -2, it's gonna go like this.
Okay.
It's not the same. You see?
So the first
Basically,
one,
it's M is not going to be the same for both no, for both sides. You can test it. You can check it by yourself by sticking in value into the limit. Let's say -1.9 and -2.1. Okay. And this function that you see here, it's a modular. That's how you can get this type of stuff. Okay. So it's gonna be y equals modular x. That's when you're getting this break. And remember, whenever you see this break, it's not differentiable at the peak, at this point where it basically bends for a sharp corner. That's another way how my professors taught me. If you see the sharp corner, then the function is not differentiable, because you know functions, it's like a real world stuff. It's always smooth. It should be smooth. It should be like rational, right? Because if you jump, if you walk, you're not jumping between dimensions, right? You're not jumping between points. If you walk, you go steady, right? You keep walking. Think about this rule in a way, like if something looks not natural, like what principle in real life would look like this? Well, what is that? Looks weird.
Yeah. So the first one is not differentiable.
At the point,
-2.
yes. And in test, you're gonna have this question: at what point the function is not differentiable?
And then B is also not, because kind of jump.
Yes.
So it's at the point 2.
If
Oh, no, for
you-
B.
it's for B, sorry. Yeah. Here we have it's called infinity problem. So from here you're approaching positive infinity, and from here you're approaching negative infinity, you see? And you can say right away that the limit of this function is not going to be the same from both sides. And furthermore, when x equals 2, function is not defined. This would look, this function, I bet it looks like this: 1 divided by x minus 2. You see, if x equals 2, it's 1 divided by 0. Do you see that?
Yeah.
And if you see 1 divided in a practical example, if you see 1 divided by x somewhere where you see x in the denominator, right away, remember at school when you were solving simple task, you would say x is not equal 0. Do you recall that?
Yeah.
Because at school they won't say you, because we're getting infinity, blah blah, because it's so hard. The true reason is, yeah, you're getting this problem. That's why you x is not equal 0. You see?
Yeah.
So it means for this one, x it does not equal 2.
Yeah.
So anything that can give you 0 in the denominator, say that if x equals this value and we get 0, then it's not true. X cannot be this value. And it's pretty much the same for derivative. Derivative won't exist at 2, right?
Yeah.
And here derivative won't exist at 0.
Yeah.
So you kind of can look at the numbers at copybook and say right away, without looking at the graph and stuff, if you see 0 in the denominator, no derivative at the point, but derivative exists to the left and to the right from this point.
Yeah.
Even though, yeah.
For question C, that's differentiable.
Yes, exactly.
And then D is not.
Yeah.
C is differentiable.
E.
Sorry.
Yeah.
And F is differentiable. Or actually, no, it's not, because you can't get anything to the left of 2.
So you would say that this function is differentiable for x
greater than
You
2.
see here is if it was like point like this,
Yeah,
you would say x greater than 2. If you don't see empty point, the hollow point, just x greater or equal to.
yeah.
This is the domain where the function is differentiable.
Yeah.
So let's take a break, okay? Think about this one if you want, or just chill for a bit, okay? Let's how much? 7 minutes, okay? So
Yeah.
we can finish faster.
Okay.
Great. See you in 7 minutes. Oh, hello, Yusuf. Hello, Yusuf.
Hello.
Hi there.
Hi, how are you?
All great. How's your day?
I'm good, you?
Yeah, fine. Almost got trapped under tons of snow today.
Yeah, me too. My power went out and I couldn't join for like a little bit, then it came back.
That's weather is crazy today.
Yeah, I know.
So, while we're waiting for Alan to come back from the break, let me give you a quick review of what we covered, okay?
Okay,
Take a screenshot or something of this task practice.
okay.
Task with same idea is gonna be a test.
Yeah,
The only numbers are gonna be different, okay?
okay.
Um, this is about average rate of change between 2 points. It's not a limit function, but it's a function of fo x2, okay? Subtract fo x1 divided by x2 minus x1, okay?
Yeah,
And you just sticking this formula here and here, and you need to define what x1 and x2 is gonna be for you. In this case, we are dealing with time. So x1 is going to be seconds and x2 are going to be seconds. For A, the first second, it means that from the 0 second to 1 second. You see, T1 would be equal 0 because it's the first second of a flight of the rocket, okay?
okay, yeah,
T2 would be equal 1. For this, for second, T1 would be 1 and T2 would be 2.
okay.
Because during the second. So you got it?
Yeah, I got it.
I'm also gonna post it online, just look it through.
Oh, yes.
This one, um, don't care about it. This is not gonna be on the test. Here, this is going to be on the test. I'm gonna ask you at what point this function is not differentiable, okay?
Okay, yeah.
Do you remember the property or the rule of existence of the derivative?
Yeah, I think I remember it. I have it down here somewhere.
So yeah, I'm just gonna talk it through real quick. First of all, I gotta remember that the limit from both sides when you approach this point should be the same. So when you approach it from positive direction or negative direction, the limit function should be the same.
Yeah,
The result of the limit function. And function should be determined at this point. You see, if you have like this round circle,
yeah.
like empty circle, it means point does not exist. So derivative at this point also won't exist.
Okay, yeah.
And what else? So one more convenient rule. Oh, hi there. Just Yusuf was us just giving a quick review of what we covered. So one more useful rule to remember that if you can draw a graph without taking the pen off the paper, it's going to be differentiable.
Okay,
So if you gotta make a jump or make an empty spot, or even you see like this example where like this one, B example, when we have infinity, we talked about that this function is going to be y equals 1 over x minus 2. And you see when x equals 2, this point, the denominator equals 0. So that's why we're getting this infinity problem.
yeah.
And in general rule, if you see that the x is in denominator, and you can find the value of x when denominator equals 0, it would mean that the function is not differentiable at this point.
Okay, yeah.
Great. So now we stopped at this. Does the function f of x equals x to the third power ever have a negative slope? If so, where? Give reasons for your answer. Think about it for a few minutes, and then I'm gonna give you a right answer, okay?
Okay.
Well, it's yes.
So, do you have any ideas?
Yeah,
Oh, I'm not so sure, no.
it's yes, has the negative slope.
I'm sorry.
It has a negative slope.
So it's gonna look this function. Oh, wait. It looks like this.
Yeah. So the negative slope.
Uh,
What?
like this, okay? Crosses and the 0, y0, x0, and
Actually, no. It doesn't have a negative slope because if you're reading it from left to right, it's always increasing.
absolutely. And how can you prove this reasoning?
Yeah, because it's always increasing from left to right.
The way I would prove it, you see, we have kind of like symmetry here
Yeah.
in 0. I would, first of all, I would evaluate the slope at 0, and at 0, at this point, instantaneous rate of change would be equal 0. Because derivative of this one using the power rule is going to be 3 times x squared, and derivative at this point if x equals 0 is also if x equals 0, derivative is also equals 0. You see that?
Yeah.
Yeah.
So we're going to have a horizontal line tangent to the graph at this point. And now let's take point here somewhere and point here. Let's take -1, oh, 1 and -1, okay? 1 and -1. So if you look for derivative at this point, you stick in this value here, right?
Mhm.
And you get f prime to x equals how much?
Um. 3.
Exactly. And if x equals 1,
3.
exactly. Same. And can you
Oh,
tell me
okay.
why?
Um.
Because we have square. And square makes any negative number positive number. So no matter where we pick our number on the like whole range of axes, no matter where we pick it, it always gonna indicate that the graph is growing at that point.
Uh-huh.
Where it gets like super steep, can you tell me? where we're basically where is this line that we're never gonna cross?
Probably at 2.
Hmm?
2. And
No, but because at 2 we still have value of a function. At x equals 2, function would be y equals 8. This line is gonna be when we have it travels to infinity so fast, you see, so fast. And for this case, this like graph is gonna go drastically up as we approach infinity, you see.
Okay.
So it's basically always gonna grow, because if you take any value of x, any, when I say any, I mean it, you see. Wherever you take, you can evaluate it, and it's gonna be bigger number, it's gonna grow. So yes, great. Basically, explain what would happen if the graph would look like this. Just give me a second. Let's say like this. Would it be differentiable at any point?
No.
And I'm gonna try to make it even more clear.
Like sharp turns, then yeah, it's non-differentiable.
I want you to recall the property of function, that function is a dependence of the variable and basically the function, right? Where for any value of the variable, you have only one value of y. You see, you have only one value of function. Here
Okay.
you can see that for x equals 0, for an instance, I just drew it bad. So imagine if it basically goes along the vertical line all the way here, and then keeps going forward. So
Okay.
here, basically, function is not defined at this point because we have vertical line and many and one x, which is 0, like gives us multiple values of the function, you see? And it means that if function is not defined at this point or does not exist at x equals 0, it means derivative also does not exist at 0. But it would exist to the left and to the right from this point. Make sense?
Yeah.
Perfect. Next one. Sketch the graph, calculate the slope of a tangent to f for just the function that we discovered, you see? At a point with x coordinate. Calculate the slopes of a tangents. So what A is pretty simple. We already did it, right?
Yeah.
B, calculate the slope of a tangent. We know slope of a tangent is a derivative of this function, right? Or f prime of x. Using the power rule, it's going to be 3x squared. And now at points with x coordinates, simply substituting x for -2, -1, 0, 1, 2, and you're going to write f prime -2 equals 3 times -2 squared, prime of -1, the same principle, okay?
Yeah.
Sketch the graph of the derivative function. How would you sketch the graph?
Hmm.
You look here. The very first line where we define the derivative itself. This is already the function of the derivative. You see?
Yeah.
Because it has x, the variable, and dependent function. It's already going to be a graph, and right away we see it's exponential. It's going to be the parabola looking up because it's not negative. You see, we just need to find 0, the bottom point of this parabola is going to be at 0, right? It's going to look like this.
Okay.
So this is the graph of the derivative f prime of x and x. Even though the graph of the function looks like this. Remember, x to the third power looks like this. And another way to see that derivative is never gonna be, that the slope is never gonna be negative, by looking at the function of the derivative. Do you see that function of the derivative never takes negative values? What we can see here that as we get closer to 0, the speed is decreasing. You see, we're basically rocketing down, rocketing down. But here we start getting slower, and as well as this graph, you see, fast growth, slowing down here. Slow acceleration, but getting in a normal speed here. Same with this graph. That's what you can see from it. Compare the graphs of f of x and the f prime x. You see? That's the comparison. You're just gonna say that like based on that derivative function of the derivative does not take any negative values. We can say that our initial function always grows.
Okay.
That would be the comparison, like what we see in common. And here, another thing. Here you can say that this is f prime x, right? Value at this point, right? This is f prime some a, okay? Some a that is here. And you definitely can see that this point is less than this, right?
Yeah.
So it means that the slope is changing and it's becoming less steeper, right? Because the derivative or the slope is getting lower. Lower and lower unless we reach 0 in 0, and that's where the graph goes horizontally. And here on the opposite side, you can see that the function begins to grow faster and faster with every step. Do you see that?
Yeah.
Great. Any questions about this?
No.
No.
Okay, perfect. This is the summary. You're gonna have this one you're gonna have in test. I kind of like it. This you're gonna have like the structure is gonna look like that. We're gonna start with many short questions, like just find the derivative or write the limit at the point. Okay, just one line solution. It's gonna be most part of a test. And then you're gonna have few tasks like this one, for an instance, with A, B, C, D. You see?
Okay.
You also may have this one. But in this one, you just need to write that here answer would be A, x does not equal -2. Or you can write in words, function is differentiable at region x less than 2 and x. Do you remember how to write and symbol? And like this.
Oh, yeah.
x greater than -2. This would be like the range where the function is differentiable.
Mhm.
And this would be a point where a function is not differentiable.
Okay.
For here, this point would be x does not equal 1. For this, x does not equal 2.
Okay.
Great. Yes, just print out these formulas for yourself. Here, you have an example of how to solve basically how to find the derivative of a function when you have a variable in the denominator. When you have it in denominator, simply raise it up by adding a negative power, right? And treat it as normal power rule. But does make sense?
Yeah.
Perfect. And now I would like you to solve this. Let's solve two equations. You pick whatever you like.
Let's do A and E.
Perfect. You want me to solve it real quick, or you want to practice? Or you're gonna practice before the test on your own?
I want to practice. Oh,
Okay, perfect.
Yeah, me too.
So for A, you're gonna write h prime x equals the first one. The simplest way is just open the brackets, okay? Harder way is to treat it as a product of two functions, f of x and g of x, okay? We also have a chain rule, remember?
Yeah.
If the product, it means derivative of the first one times second function, subtract plus or subtract derivatives of second one times the first function. But for simplicity, why would we do that? This one can be treated as 2 times x a square, multiplying by this, plus 8x, multiplying by this. Now this pair plus 3x plus 12. And makes sense why this line looks like this?
Yeah.
And now don't forget, it's not derivative yet. We just opened the brackets. So put the brackets and denote it as prime notation, okay? Next step would be to treat them as a sum of functions. This would be exponential. You're gonna use power rule. This would be just a simple function. We're also gonna use power rule here, and this is constant rule. Remember, derivative of a constant is equals to 0. So it's gonna be 4x plus 8 plus 3 plus 0. Simplifying it, it's gonna be 4x plus 12. This is the derivative. And to make sure you are correct, it is enough
plus
to look.
11.
Huh?
It's plus 11.
Oh yeah, you're right. 8 plus 3 is 11. So to determine whether you did everything right, just take a look at the power. Because remember, when we taking derivative over something to the second power, derivative is going to be of a first power, okay? And it's pretty much the same with any other function.
Mhm.
Derivative of an exponential function is always going to be 1 power less, or n minus 1 power. Remember this power rule. So did you wrote it down?
Yeah.
Great. So yeah, how to check yourself? You look at the event final formula, you see first power, and if you look here, it looks like it's pretty much like x plus 4 a square, like yeah. Also if we expand it, it's gonna be x plus 4 times x plus 4. Also 2 brackets with x in there. And we know that this is actually a polynomial function of second power. Do you recall it? This is going to be
Yeah.
x squared plus 8x plus 16. And if you open these two brackets, you can see we have second power here. So we checked, all good, derivative is right. Example E. G of x is equal 5 times x squared to the power 4. First, the simplest thing I can do is simplify it. And I'm going to open these brackets by bringing x squared to the fourth power. And when we multiply, when we bring a power to the power, powers are multiplied. 5 times x squared times 4. So it's going to be 5 times x to the 8th power. Make sense?
Yeah.
So now the derivative or the g prime of x is going to be 5 times 8. This is n that goes in front. And x to the power 7. It's going to be 40x to 7.
Is it 8 or is it 6?
This is 8. Because it's a product, not a sum. Product because if something is raised to the power twice, the power multiplied.
Okay. And then if it's added, you add the powers?
If it's added, you should have the same. No. When it's when x squared times x squared, you sum up the powers.
Okay.
2 plus 2. If x squared to the power 2 is going to be x squared times 2 also equals x4. It's just, if you take another example, answer would be different. If you take 3, it would be 6. If you take 3 here, 3 and 3 is going to be 9. You see?
Yeah.
Any questions about this example?
No.
Let's solve f, okay? F is really important. So right away, we see for t greater than 0. Okay, perfect. Now we're going to look at t greater than 0. Now let's find the derivative of this. Derivative of something like this. We can represent it as derivative of f of x. Oh, sorry. F of x divided by g of x, okay? And this is all under prime notation. Then the next step, it would be f of x derivative times g of x subtract f of x times g derivative x divided by g x square.
Okay.
Double check this rule. It should be called coefficient ruler, I believe. It should be in last week slides. Remember, I inserted all the formulas. All of
Yeah.
them are there. So can you solve, knowing this, can you solve it for me? Anyone?
Mm,
We gotta round up already, so it's okay. I'm gonna do it. Just while I'm solving it, please Google derivative of a fraction.
Okay.
Double check it. Go ahead and investigate it. So it should be derivative of f of x, which is on top, times g of x. So it's going to be derivative of these brackets. And we treat it as difference of derivatives, right? Pretty much easy. Both of them are under power rule. And on practice, in real life, you're going to use power rule a lot. So it's going to be 5 times t to the fourth power, subtract 6 times t. Make sense?
Yeah.
Next one, times 2t. Subtract t to the fifth power, 3t squared, times 2, because derivative of 2t is 2, divided by g of x squared. Okay, g of x is 2t, so it's going to be 4t squared. Make sense? Any questions so far?
No.
Do you understand my calculations?
Yeah, I understand.
Great. So now, next step would be to open the brackets and simplify what's possible, okay? So it's gonna be 10t to the fifth power subtract 12t squared subtract. Now, keep in mind, these are brackets. First we multiply and then we open the brackets using the minus and changing the symbol inside. So it's going to be 2t to the fifth power plus 6t squared. Any questions?
no.
No.
4t squared. And now 2t to the fifth power. So we simplify like this. This is going to be simplified. This is going to turn into 8 to the power t, 8t to the power 5. Do you see it? Common terms grouping up. So, and we end up with just moving a little bit. And we end up with 8t to the fifth power subtract 6t squared divided by 4t squared. And what would be the next step, guys? Simplify it.
Simplify, yeah.
By how?
By
Oh, you would
factor or no?
yeah.
Yeah, factor.
Yeah, greatest common factor.
Yeah.
Now we see boom, 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 boom. 4t to the third power minus 3 divided by 2. This is the answer.
Okay.
And if you take a look at the initial formula, again, how to check your answer. Look, do you see it now? So here, you also can simplify t, right? And the greatest power you're gonna get is gonna be t to the fourth power here, right? And if you look here, the final derivative we got, the greatest power we have of t is third power. And again, it complies with our principle that derivative of any exponential function is going to have the greatest power, one less than the previous one, the initial function.
Okay.
Any questions about this?
No.
So thank you, guys. I'm going to pause the practice test for you. It's not going to be hard, I promise.
Okay.
You're going to have a few. Oh, you see product rule. Product rule and this one. Oh, product rule and coefficient rule. I just forgot how it's called. The one we used in this example, F. They're somehow similar.